Okay, next up, velocity and speed in 2D and higher. So we'd previously very quickly talked about if we had two position vectors, an r1 and an r2, and those of course result in some displacement delta r. Well, effectively, the average velocity is just that displacement vector divided by the elapsed time, and the proper instantaneous velocity vector would just be the derivative of the position vector with respect to time. So there you'd be looking at a tiny change in the position with respect to time. All right, we can split that out into components. It would be dx dt in the I hat plus dy dt in the j hat. And this becomes important later because we'll just divide things up. We'll take all the x stuff, all the y stuff, and handle them separately, and then bring them back together at the end if we need to find the vector result. So either way of writing this is perfectly fine. Speed remains the magnitude. So speed is just the magnitude of the velocity vector. And that would look like taking the absolute value of it, but its physical meaning would be taking the dot product of the velocity vector with itself and then the square root, or vice versa. It would be dx dt the whole thing squared, not second derivative, just squared, and dy dt the whole thing squared, and then take the square root. Okay, I said this would be fast. This is really all there is to velocity and speed in 2D and higher order dimensions. If we were in the third dimension, we'd add a plus dz dt k hat. We'd add another term here. It's basically the distance formula because it's all like triangles in higher order spaces. So you're just finding the length along the hypotenuse, basically. All right. If you have any questions later, please let me know. But this is going to be it for the instructional video on velocity and speed in 2D and higher. Next up, acceleration.